Hi, everyone. Welcome to Beaconr's webinar series, and thanks for joining. Today, I'll be talking about dependency graphs, so what they are, why they're useful, and how they work in Beacon. My name is Mark Higgins. I'm a co-founder of Beacon and our Chief Analytics Officer. A quick overview of the talk today. I'll start off by talking about dependency graphs in Excel. That's because that's what people are most familiar with. And we'll look at some simple calculations and some financial calculations. Then we'll switch over to Beacon's dependency graph framework, which is called Grommet. And we'll talk about how that works and how dependency graphs are implied from object-oriented Python code. We'll look at some financial examples of that using Grommet graphs. And then at the end, we'll talk about a separate use for Grommet inside of Beacon, which is as part of our application framework, which is called Glint. And we use Grommet there to signal between different UI components. But let's start off with Excel. Most people are familiar with Excel, and Excel is sort of the quintessential dependency graph. It's got this dependency graph at its core, and that's one of the main reasons people find spreadsheets so useful. So let's switch over to Excel spreadsheet here. I'm just going to put in cell B1, I'll put in a value of 1. I'll put a value of 2 in cell C1. And then I'm going to put a formula here in A1, which is just going to be B1 plus C1. Behind the scenes, Excel has now constructed a dependency graph that says I've got two inputs, these numbers that are kind of data, and one calculated value, which represents, which changes when the inputs change. So if I change the value of C1 from 2 to 3, then you can see A1 automatically changed. And behind the sheets, Excel knew that A1 needed to change when C1 changed because it has this dependency graph. So if we think about that in sort of dependency graph diagram, I've got a picture here with cell A1 that's got a red background to show that it's a calculated value. Cells B1 and C1, which have a gray background to show that they're input values. And the arrows here show the directions of the dependencies. So A1 depends on B1 and C1. And of course, we can do something slightly more complicated, like if I put in a value of 5 in cell D1, then I'm going to change C1 to be, say, D1 times 2. Now I've got a bit more of a complicated dependency graph. A1 here still depends just on B1 and C1, but I've got a little bit more of a complicated structure where now I've got A1 and C1 are calculated values and B1 and D1 are the inputs. People often use Excel for financial calculations, partly because of this dependency graph. So let's imagine a use case where you're using Excel to track the value of a portfolio of equity options. So you can imagine there's maybe like a table of positions, which with one row each for each option position, a table of market data inputs like stock prices, implied volatilities, and then formulas in some of the other cells that calculate the value of each option and sum it up to get the portfolio value. So let's take a look at that in Excel. Here's a little spreadsheet where, again, I've got a table of positions that define which options trades I have on. So this one, for example, I've got my equity is this fake equity ABC. It says here's the expiration date, strike price, whether it's a call or put option, and the number of shares here. I've got another table of inputs, which are the market data inputs. So I've got for each of my 4 equities, I've got the stock price and I've got the implied volatility. Now, for people who know stuff about derivative stuff, you know that there isn't just one implied volatility per equity. There's a separate implied volatility for each expiration date and strike price. We're going to ignore that complexity here and just pretend there's one implied volatility for each equity. So again, I've got my inputs with this kind of gray background here, and I've got calculated values with this red background. So for this particular row here, I've got the stock price, which looks up the stock price in this table, timed expiration, which is calculated between the expiration for this option and another input, which is the current date. Then I've got some intermediate value calculations here, D1 and D2. These are inputs into the usual Black-Scholes formula for an options price. And that's what I've got here is unit price. This is the price for an option on one share of stock. And then the position price is that unit price times the number of shares in this position. Then I've got a total value of the portfolio, which just sums up all those individual position prices. This is useful because I can do things like say, well, what happens if like the ABC price were to change? So if it changed from $25 to $27, for example, then I can just put in 27 here. These rows that depended on ABC, they changed. The other ones didn't change. And one interesting thing about dependency graphs is it gives you kind of optimal caching. So when I changed that ABC price, these rows recalculated, these ones didn't. You know, you might have thought maybe they just recalculated to the same values, but that's not what happened. Excel's dependency graph realizes that all the things that don't depend on the ABC price don't need to recalculate, so it cached their values. So if those were expensive calculations, you could, you know, save a bunch of calculation time. But the ones that do need to be recalculated get recalculated. Also, I got these intermediate values exposed, D1 and D2, and that's useful because for debugging purposes. So if something looks wrong, I can kind of drill into all the inputs behind the price exposed in different cells in the spreadsheet. Makes it easier to debug. We can see the dependency graph a little bit. Like if I go in here and I go to the formulas tab and I do trace precedence, this shows me what cells this total value depends on. So we can see the formula here is this the sum over all these rows. And so you can see what that depends on. Similarly, if I look at, you know, the position price for this one row, I can do trace precedence and it shows me that it depends on the number of shares in the unit price. It's just the product of those two. Then if I hit trace precedence again, I can kind of step down one level in the graph. And if I keep on going, I can kind of see all the things that depends on. It depends on stock price and implied volatility in today's date and contract terms for that option. So that's a really useful tool in Excel for being able to set up calculations, debug them, and run them efficiently, do that kind of optimal caching. Now, one thing you might want to do in an example like this is figure out your risk position. So what that means, say I want to calculate the delta of my portfolio to each one of my equity names. What delta means is how much does my portfolio price if that underlying equity price moves up by $1. So let's try that. The current price is $351. You know, I can see that up here in the top. Now, if I go and change ABC, I'm going to move that price up by $1. And so now the price moves to $272. And so I can calculate the delta as just kind of the difference between those two numbers. So I've got a minus $79 per dollar delta to ABC stock price. I can set it back and then do the same thing for, you know, DEF and calculate the delta for that. And I could do it for the other ones as well. But it's kind of manual. I have to kind of manually go and do all those risk calculations, those bump and reprice kind of risk calculations. So let's think about, you know, in the context of that example of that spreadsheet, some of the benefits of a dependency graph. So the first one is this optimal caching idea. So there, when an input changes, like a piece of market data, for example, only the values that depend on it get recalculated and everything else is cached, so it doesn't need to recalculate. A second use for dependency graphs is dependency tracking. So for a given calculated value, like the price of my portfolio, which inputs does it depend on? So if I want to find out which equity prices out of all the universe of equities does my portfolio value depend on, so they can go and figure out which ones to go and calculate delta with respect to, for example. You can kind of descend down through the graph and look for those inputs. And then a third benefit of the graph is exposing those intermediate values as nodes in the graph, so as cells in your Excel spreadsheet in that example. So those D1 and D2 values are nice examples, or the implied volatility or the stock price, that are the inputs into other calculations. And having that exposed means it's easier to debug. Excel is really powerful. It's probably the most popular risk management tool on Wall Street right now. But it does have some downsides, and mostly around the fact that Excel is this kind of largely unstructured grid. That means it's not a great tool for enterprise development. It's easy to build simple things, but it's hard to kind of build and maintain and extend complex spreadsheets. Part of that is because it's difficult to make modular functionality. Like we saw in that spreadsheet, functionality is kind of spread through calculations in all the different cells in the spreadsheet, rather than in well-segregated modules that are easier to maintain. And that makes it difficult to support. A spreadsheet, I'm sure you guys have all seen this before, you know, a spreadsheet that starts off pretty simple to solve a particular business problem it tends to get more complicated through time as people add functionality to it. Performance starts to suffer. You end up like having to buy a special high-powered desktop computer to be able to open your 5 GB spreadsheet. If the original developer who designed that spreadsheet leaves, it's difficult for someone else to come in and pick it up and understand all the nuances and figure out how it all works. So it is possible to develop effectively in Excel, but it's hard. It's not really designed for that. So that brings us on to Beacon and how we use dependency graphs. So Beacon has a dependency graph component inside that's called Grommet that's really designed for that kind of enterprise scale calculation. Grommet gives you the same benefits that you get from Excel's dependency graph, plus a whole lot more, but it's structured as object-oriented Python code rather than Excel's kind of unstructured grids. Grommet kind of acts like Excel in manual recalc mode. So in that spreadsheet example, when I changed, the ABC stock price, automatically all the values calculated because I was in automatic recalc mode. If I switched to manual recalc mode in Excel, then I'd have to, make it recalculate after I change values. And that's kind of how Grommet works. So values aren't automatically recalculated when the inputs change. They're just marked as dirty or invalid. And the next time someone asks for the value of one of those invalid nodes, that's when the calculation happens. All of our financial analytics that we've built in Beacon, we have a broad suite of cross-asset financial analytics. They're all based around Grommet and use the dependency graph for that. We also have another use for Grommet inside of Beacon that isn't around our financial object models, that's around our application framework. So Beacon has an application framework called Glint that makes it easy to build web applications. We'll talk a little bit more in detail about that, but that uses Grommet to kind of notify UI components when they need to update. So let's dig in a little bit more to how Grommet really works. So using Grommet means writing Python classes, and on those Python classes, some of the methods on the classes map to nodes in this dependency graph. With Grommet, that mapping is done automatically for you. It'll just parse your method code and figure out the shape of the dependency graph dynamically. You don't need to sort of explicitly manage the graph anywhere like with some other dependency graph frameworks. We've got a couple of useful helper functions for working with the graph that are available in our Beacon IDE. So one is called show graph. So show graph is a visualization for the dependency graph, kind of like what we were looking at when we were looking at that A1, B1, C1 graph with the arrows between them. It's useful for smaller graphs. We have another function called show node, which lets you visualize a specific node in the dependency graph and see what it depends on, what depends on it, its state and all that kind of stuff. So let's jump over to our Beacon IDE here, and we can take a look at some of those examples. So what I've got up here is the Beacon IDE, and I'm looking at some Python code, right? So we've got a Python editor up here. We've also got a shell where you can kind of interact with data and objects that you create. So here I'm going to start off by creating a simple class. It's called simple, that uses our dependency graph framework. To use it, all you basically have to do is inherit from this base class grommet.object. This class has 3 methods, A, B, and C. And you can see they're all tagged with this decorator, grommet.fn. What that means is the method that I define next is going to be hooked into a node in the dependency graph. So with Grommet classes, you can have a mixture. Some methods are linked to nodes in the graph, and others are just regular Python methods. I've got 3 methods here. One of them is calculated, this method A, but the other 2 are inputs. So to tag something as an input in Beacon, you pass this grommet.stored parameter into grommet.fn, and that means this method is something you can explicitly set as something that gets serialized to the database if you were to create one of these objects and save it out and that sort of thing. But it can have default calculations, so if you don't explicitly set the values, that's fine, it'll fall back on the default calculation. So I've got B here, which defaults to 1, and C that defaults to 2. A is my calculated value. So here, A is just going to equal B plus C. Notice I haven't sort of separately specified the shape of the dependency graph. What happens is when I define this class, it parses this method code here and recognizes that B and C are children of A. So I've got this method code for A that's hooked to a node in the dependency graph called A, and it recognizes that node A depends on the values of B and C. So let's play around with this. Let's, first of all, I'm going to parse this class. Then I'm going to construct an instance of this guy. So here I've created this object S, which is an instance of this simple class. Note that it's got a name. All objects in B can have names, and we'll talk about that in a minute. Because I haven't explicitly specified a name, it gets a default name that lands in limbo and has some unique identifier here. I can go and look at the input value. So here I'm going to look at B. It's equal to 1. I haven't explicitly set it, and so that means it falls back on the default calculation. I can do the same thing for C and see that that equals 2. Now I can call our calculated value. So I'm going to call s.a, and it returns sensibly B plus C equal to 3. I also, when I define the method for this thing, I put a little print statement in here just to have it print out when it's actually calling this method code. So the way that evaluation works with Grommet methods is a bit different than standard Python methods. What happens is when you call the value of A, for example, it indirects that call over to the node A that is associated with this method. And it says, node A, have you already calculated yourself before? And if so, it'll just grab the cached value off of that. That's the optimal caching part of the graph. But if that node does need to be recalculated because it's never been calculated before, or because of one of its inputs has changed since the last time you calculated it, then it says, okay, well, now I actually need to do the calculation. And so that's when it actually calls this method code. So the very first time I call A, it hasn't been called before, so the node is marked as invalid. So when I call A, it actually has to call this method code. But if I call A a second time without changing B or C, you notice it prints out 3 here, but it didn't print out in A. And that's because the second time it went to that node A and said, oh, the node value is already valid. I just have to grab the cached value. I don't actually have to do any calculations. And that's kind of the core of that optimal caching bit for the graph. Now, if I go and explicitly set the value of B, if I change it from 1 to 4, I can do that with this syntax. s.b.set value and pass in what thing I want to set it to. If I now look at the value of B, it comes back as 4 as I expected. And if I call s.a again, well, now because one of the inputs of A has changed, when B changes, it kind of goes up the dependency graph and marks everything that depends on it as invalid or dirty. That means the next time I go and ask for A's value, it says, well, I actually have to do the calculation. So it calls this method code, and that's why it prints out in A here, before it returns the value of 6. If I call s.a a second time, again, the second call is cached, so it didn't print out that little message in A because it never actually had to call this method code. It just returned the cached value. All right, so that example looked at kind of a single Grommet object and dependencies between methods on that single object. And that's interesting, but kind of limited. It's kind of like that unstructured grid idea in Excel. Real applications with Grommet have multiple different objects, and those different objects encapsulate different bits of functionality. That's the kind of part of object-oriented coding that lets you have nice little modules of code that are easier to maintain and support on their own. So Grommet supports this, and in Beacon we have an in-memory namespace connected to an object-oriented data store that lets you define well-named objects. And then the way that you define dependency graph connections across objects is just by accessing those objects by name. So let's take a look at an example of that. So here's another script, which is a little bit more complicated. So this is going to follow our equity option example that we looked at in the Excel spreadsheet. So it's going to do something along those lines. So I'm defining in this a bunch of different Python classes. First of all, I've got this class global parameters. So this is going to be a well-named object. It's going to be called global parameters. That's going to hold kind of system environment information. In this case, it's just going to have one piece of data, which is the today date. So I'll go and parse that class. I've got a second class here that represents an equity market. So in Beacon, we have this notion of market interfaces, which are classes which kind of aggregate all the information you care about at the level of a particular asset. On this one, just like our Excel spreadsheet example, it's got a pretty simple structure. I've just got a bit of input data, which is the stock price, and another bit of input data, which is the implied volatility. Then I've got a third class, which represents an equity option position, okay? So this has a bunch of inputs on it which correspond to the contract terms, like, what's the underlying ticker of the equity, what's the expiration date of the option, what's the strike price, is it a call or a put? And then it's got some calculated values as well. An interesting one here is this equity obj method, which returns a reference to a well-named object. So in Beacon, we have this underlying data fabric, which kind of looks like a file system. So it's got directories and subdirectories, but instead of files, the things are objects. And so here it's saying, give me a reference to an object in the equities folder, with the name of the equity that I depend on. We've got another method, timed expiration. We've got some intermediate values, D1 and D2, just like we had in that spreadsheet. And then we've got the premium. So let me parse this class. Now we can do some interesting stuff with it. So I'm going to start off by creating some objects with proper names. I'm going to start off by creating this global parameters object. When I created an object before, I used grommet.ns.new, which creates a new object. Here I'm using another method, lookupperNew, which says I want to create a new object, but I want to explicitly name it. So if we look at that object down in the shell, here it's showing me, the type of the object and what its name is, and now it's got this proper name, global parameters, in the kind of root of our file system. Then I can go and create an object that corresponds to one of these equity markets. And here I've gone and set, one of the inputs in line, as I create it. I set the stock price equal to 20. I didn't set the implied volatility. If we go back up to the class definition, it's got the stock price and the implied volatility. I explicitly specified the stock price is $20, so then it won't use this default. But I didn't explicitly specify the implied volatility, so it will use the default. So we can print out the stock price here of $20, which is what I explicitly set, and we can print out the implied volatility, which I didn't explicitly set, so it falls back on the default. And this equity market object, again, is a well-named object. It's in that equities folder, and it's got, the name of the, named by the ticker. Then I can go and create one of these equity option objects. If I look at this guy, I didn't give it an explicit name because nothing in this example is going to reference it, so I don't need to bother naming it. So it's got one of these default names in limbo. Again, I specified, some of the inputs here, but I didn't specify all of them. And then I can go and say, what is the that equity obj thing, the thing that points to, another well-named object. And then I can go and calculate the premium. Maybe I'll step back and just walk through how these calculations work. So here's one of our methods, which is the time to expiration. So this is the actual 365 time from today out to the expiration date of the option. So when the Grommet parser runs through this code, it figures out the shape of the graph. And the first thing it does is it says, well, I've got one dependency, which is on expiration date, which is on myself, so on the option object. And then it's got another dependency, which is the today method on this different object, this global parameters object. And the way that I connect this option object to this different object, the global parameters object, is just through naming it, getting a reference to that object and naming it. If I look at the premium calculation here, here it's going to print out a little message in premium, similar to the in a print that we did in the previous example to show when it's being calculated. And it grabs the stock price, strike, D1 and D2, and calculates the premium. So if I call that premium method here, it assigned that to this variable prem, and that's got the premium of the option, but it also printed out in premium. And that was for the same reason as when we were looking at the simpler example before, because this premium calculation had never been done before. So by default, that node is marked as invalid. The first time you call it, it says, okay, I need to do the calculation. It actually calls this method code and does the calculation. But if I call that calculation again, it returns me the same premium, but it didn't print out this message in premium because it didn't need to actually execute this method code. The second time, when it went to that premium node, it said the node is valid. That means I can just grab the cash value and don't need to do any calculations. All right, so now I want to talk about a slightly different topic, and this is something that kind of is an example of how Grommet's graph is more powerful than Excel's dependency graph. In Excel, it's difficult to kind of automate the calculation of the deltas that we saw before. You have to kind of manually bump the inputs and manually track the price changes. Grommet lets you do this programmatically through something called overrides. The idea with an override is it's a temporary value that you overlay on a node for some defined part of the execution. When you put on an override, all the nodes that depend on it are marked as invalid. And then when you ask them to be calculated again, they recalculate using that temporary value. That temporary value, though, is applied inside a Python block. And when you leave the block, the node's original value is restored and all the things that depend on it are invalidated again. So it makes it really easy to do those kind of bump and reprice calculations. And these overrides form the basis of Beacon's risk calculation framework. So if we come back to our little option example here, I've got this with Grommet.context block. Inside this block with Grommet.context, any overrides that I apply are valid only for the lifetime of this block. And when I leave the block, they're taken back off and the original values are restored. So inside this block, I'm going to bump the stock price up by a little bit, by 1 cent. So I'm going to override the stock price method with a new value, which is the original stock price plus a little bit. And then inside that block, when I call premium, it's going to recalculate the option price using that shocked price. So let's run that little calculation here. So it ran those 3 lines. It applied that override, and then called the premium calculation. And so again, it printed out this little thing in premium because inside that block, that with Grommet.context block, it had applied a different stock price. And then when I went and asked for the premium, it said, oh, I'm invalid, I need to go and recalculate. And when it pulled in the stock price, it pulled in my override stock price. And so I can look at the value of prem up here, and it is a little bit bigger than the premium before. And then I can go and calculate the delta as just kind of the finite difference. So that's how you do kind of basic risk calculations inside of Beacon using overrides, which is a really powerful feature of the graph. Beacon has a risk reporting framework that basically lets you define a tree of different market scenarios and then risk values to calculate in those. So you might say, I want to calculate, delta, gamma, vega, and theta for an options portfolio, and do that in a bunch of scenarios where my asset price is shocked up and down to get kind of a ladder of risk. So Beacon's risk reporting framework makes it really easy to do that kind of thing. And behind the scenes, it's all implemented using those Grommet overrides. It works for scenario risks like deltas. It's also really useful for P&L, profit and loss reporting. So P&L reporting shows how much money you made or lost on the day in total, but also how that P&L is allocated into different market factors. And a dependency graph makes that calculation really straightforward. So if you imagine I'm going to start my environment at like last night's close, so last night's date, as well as last night's market data, then I can go and say, well, let me take my today value and move that forward from yesterday to today and recalculate the price. And the difference versus last night's price is going to be my time P&L, like my theta and carry and stuff like that. Then I can go and say, okay, now let me take all my equity prices and shock them from my values in last night's close to the current values, price it again, and the difference in price there gives me my P&L due to equity price moves. And then I can say, keeping the equity prices at their new values, move all my implied volatilities from the old values to the new values. Price it again, and the difference in price gives me the P&L that I get from implied volatility moves, and so on until I've shocked each piece of market data. So that's a really nice, clean way of doing P&L explain that's really easy to do when you have a dependency graph like this. The graph also lets you decide how to parallelize really effectively. Grommet programming, even though it's written in Python, is a lot like functional programming. And nodes calculation is kind of a pure function. So the inputs can be serialized and then sent out to a remote calculation engine. Last thing I wanted to touch on is a slightly different use for Grommet inside of Beacon, which is as a component of our application development framework, which is called Glint. So in Glint, the idea is, like I'm a quant, I don't know JavaScript, I don't know really how web applications work very well, but I can write a fully featured enterprise web application in Glint just by kind of scripting out a grid of widgets in Python. Hit F9 and dynamically it converts it into an enterprise web application for me. Handles all the complicated enterprise stuff about like making sure that there's a back-end job to do the calculations. It checks that I'm entitled to run it. It encrypts communications back and forth and all that kind of stuff. I don't need to know how any of that stuff works to build something in Glint. I can just do it all as sort of writing a user interface in Python. One part of how web applications work is, imagine I've got an application which is like a calculator for an options price or something. If I go and change, say, the strike price of my option, maybe there's another field that corresponds to the price of the option. Something has to tell that price widget on the user interface that it needs to recalculate and show the new options price. And Grommet plays that role inside of Glint. So Glint has this model view controller model, model objects which do all the actual calculations. In Glint, those model objects are Grommet objects, so they use our dependency graph framework. And then Glint uses that Grommet invalidation to signal when changes need to be made across the UI. So for example, if I go and change the strike field in my application, that goes and it does an override on the underlying model object, where imagine I've got a Grommet class that has a strike field on it, goes and changes the strike on that, and then maybe it has another method that corresponds to the option premium, which depends on strike, and so it uses Grommet to kind of signal that premium that you've been invalidated. Now you need to go and recalculate and redisplay that in the user interface. It means developers don't need to explicitly write code to manage that signaling across user interface component. It makes it a lot easier to write applications. So let me show you an example of an application that uses that. Here is our Beacon quote application, and I've got again a kind of a real world option calculator here for some Russell equity options. And here I've got two equity option positions. For this one, which is a 2350 strike, it's got a price of $314,000, and if I go and change the price to 2360, then it goes and automatically recalculates the price. And again, this is using Grommet. As I change the strike, it passes it back through the backend process, changes the strike on a model object, which also has a value method on it, and Grommet is the thing that kind of signals value that it needs to recalculate and redisplay the values. So in conclusion, dependency graphs are really useful tools for financial analytics and for application development, and that's one reason why Excel is so popular in our industry. Beacon has a powerful dependency graph framework called Grommet. Gives you all the advantages of a dependency graph, but with the maintainability and extensibility of object-oriented Python development. Grommet's used to tie together all of Beacon's financial analytics. So in that example in Beacon quote that I showed you of like real world equity options, for example, behind the scenes, all those equity options are represented using Grommet as Grommet classes, along with the Beacon namespace and that underlying object database that lets you kind of segregate functionality into objects. Grommet's also a component of Beacon's Glint application development framework, and it's used there to automatically handle signaling between user interface components so that developers don't need to write code to do that. So I will pause there and happy to take any questions if people have them. So one of the questions that got posted, is there a mechanism to prevent cyclical dependencies, or is the system able to handle them? So Grommet does not support cyclical dependencies, and so it'll, raise an error if you design a graph that does have cyclical dependencies. I'm happy to take any other questions. If people do have them, okay, another question, is there a way to view these graphs? Great question. Let me jump back into our IDE here. So I mentioned these functions show graph. So let me look at the graph for this option premium. Actually, I'm going to explicitly calculate it first, so it's valid. If I do show graph on that option premium, then it's going to pop up a little visualization for the entire dependency graph. And so for this simple graph, it's something that works pretty well. I've got one kind of box around some, each of these individual boxes corresponds to a node in the graph. We've got these kind of bigger boxes which kind of group those things together into objects. So here I've got one box that corresponds to my option object, which has this kind of default limbo name. So it's got the premium as well as the D1 and D2 values, things like that. There's another box here that corresponds to nodes on this global parameters object, and there's just one, the today date. And then I've got another box which corresponds to nodes on this equity market interface, which has the implied volatility and stock price in it. So this is a useful tool for kind of viewing relatively simple graphs. Once you get into complicated graphs, though, like more real-world graphs, there ends up being so much stuff on this that it becomes a little bit less useful. And a better tool for analyzing that is show node, which lets you visualize information about a particular node in the graph. So if I run show node here, keep that a little bit bigger. So this is showing me information about one node in my dependency graph. At the top here, it's showing me it's on this option object with this default name. And for the premium, shows the value of the node. And it shows what things it depends on. So it depends on the stock price on this other object, this ABC object, the strike price, D1, D2, and the option price and stuff. And I can go and, for example, step into the calculation here. So if I hit enter on this D1 row, then it shows me information about that D1 node. And it shows me what stuff it depends on. For example, it depends on the implied volatility here. So we have a lot of kind of visualization tools for that. So I think there's some more questions in here. Sorry, 1 second. Let me just try and view these things a little bit better. One of the questions is, what about real-time input? Can Grommet handle that? So starting the application in the morning and seeing ticking values through the day. Absolutely. As long as the calculations that you're doing can kind of keep up with the refresh frequency of the underlying data, which is just depends on which kind of calculations you're doing. You can absolutely have a pub sub mechanism which gets updates for inputs, applies them as overrides, and then displays them. Let's see, another question. For C++ analytics libraries, are there guidelines for when to include checkpoints at which the developer should make calls to the Grommet Graph Manager? Typically, we don't use C++ like that. So we'll use C++ the other way. So for example, in this D1 calculation that I'm showing here, it pulls in, a bunch of, market data and contract terms and things like that, and then does some analytic calculation. In this case, it's a pretty simple one. You can imagine, though, that if you expose some C++ library in your environment, you could have a method in a Grommet class that grabs all the information it needs, marshals it the right way, and then passes it into a C++ library call. So that's typically how we integrate other languages like C++ or C# or a bunch of other ones into the graph. Is they're kind of leaf level calculations that take values that are pulled in from the graph and then are passed into the analytics. So another question, imagine the developer is changing their Python class and is changing the definition of a method. How does Grommet handle that? So if you're changing the definition of a method, usually what ends up happening is you just kind of like, blow your graph away and then rebuild it, to make sure that you're picking up the right state. And that's kind of handled automatically in the IDE. So if I go and change, the definition of one of these objects and reparse this code, then any existing objects that were created with the old code will still have the old behavior, but any new ones that you create will use the new behavior. Let's do maybe one more. Can your dependency graph framework work with visualizations, for example, Plotly Dash? Absolutely. So, so if we go back to our beacon quote application, for example, here I've got a chart which is showing implied volatilities by strike for this particular market. That's also sitting on top of the dependency graph stuff. So Glint's application, the Glint application framework kind of manages that interaction for you. And if you wanted to build something more bespoke that wasn't using Glint, when it was using Plotly directly, for example, then you can do that as well. So maybe one more question. Are there graph APIs available to Java, C++, or C#? Similar to the last question. So typically the way that works is you'd end up calling your C++ library once you've marshaled the data that it needs, and you wouldn't be accessing the graph from inside those other analytics. So Beacon supports integrating code from lots of different languages. So we've done C++, C#, in general .NET stuff, Java, MATLAB, R, and probably a bunch of other ones that I'm forgetting right now. All right, so why don't we finish things off there? We're at the 45-minute point, and we'll take a look at some of the other questions, and happy to answer so those other ones offline. But just wanted to say thank you very much for attending. I hope you found this interesting, and thank you and goodbye.